All right. For our next topic in design for additive manufacturing, we want to focus on product or project planning. So there are some important topics in here we want to cover. We want to talk a little bit about economics of AM, how you estimate build time for additive manufacturing, and other related project management issues. And in particular, we'll be focusing a lot on SLS because that's our technology of choice for our semester-long projects. All right, so if we think about costs of additive manufacturing, right, there are three different categories. We used to call additive manufacturing SFF, or solid freeform fabrication, so just replace that with additive manufacturing and we'll be ready to go. Machine costs, labor costs, material costs. So those are three things that we want to focus a little bit on. We've talked about material costs for sure in the past, but we'll talk about that again today in just a little bit more detail. And we'll also talk about machine costs and labor costs. And together, those three things, plus overhead and profit, help dictate the price of a part that you would order from a service bureau. According to Hopkinson and Dickens a few years ago, the typical cost breakdown for applications, right? Machine costs are going to be about half of it, materials costs are almost half, and then labor is the remainder. So it really depends a little bit on application to application, how expensive the machine is and how expensive the materials are. But in general, the machine and the materials are the bulk of it, and then the labor is a smaller part of it, especially if we're talking about plastic parts. So if we think about overall cost, polymer SLS parts from a service bureau start out at typically somewhere around maybe about $50 per inch of vertical build space that they occupy. So if you have like a small 2-inch part, you know, you might start a small 1-inch, inch and a half part. You might start by paying maybe $50 or so for that part. And then it could be more expensive depending on the complexity of the part, depending on the size of the part in the XY plane. But that's a good place to start. I used to tell people it was somewhere around $100 to $150 per inch of vertical build. But a lot of times now you can get a fair bit cheaper, around $50 or maybe even a little bit less depending on the part. Of course, that cost does depend on the complexity of the part, how much inspection and post-processing requirements there are. So if it's a really complex part that's going to be difficult to get the powder out of or very, very delicate, it could increase your costs. If a lot of inspection is required, that could increase your costs. So we saw the ferro arms and the coordinate measurement machines, the CMMs at Stratasys Direct, and if those need to be used, then that can increase the cost of your parts as well. And then other post-processing requirements. Does it need to be painted or finished in some way, sanded, polished? Does it need to be built in multiple parts, and those parts need to be assembled in some way? Adhesives need to be used to glue it together. Lot size can also be important. So how many of these parts are you making? If you're only making one copy of a really complex part, you may pay more for that part than you would if you were making lots of copies, because then you can get slight economies of scales, right? Any of the consultation work involved in getting it to print right, placing it in the build, shipping it out, all those types of things can all benefit from economies of scale. Right, so the first thing, machine, labor, material costs, right? So let's think about machine costs, right? So how much does a machine itself cost, right? So in stereolithography, we talked about these costs ranging from maybe $200,000 for a starter 3D systems machine up to, you know, almost $1 million. For SLS, the machine we use downstairs, which is a refurbished Vanguard SI2 high-speed system. A new system like that is somewhere around $300,000. It could and up depending on how big it is and how much capacity it has. For, you know, FDM machines, those can be really inexpensive if we have, you know, a desktop type system. They can also run up to much more expensive systems if we have a large capacity and the capacity to build specialty materials like Ultem. Lens machines are expensive as well. So the other factors to consider besides just the cost of the machine would be the maintenance costs. So how much does it cost per year to maintain something? How much is it being utilized? And then how long is the life of the machine, right? How long is it going to be used? Does it have an 8-year, a 10-year, a 12-year, a 5-year life? And at the end of that life, is there any salvage value to the machine, or do you assume that there's zero salvage value associated with the machine? And then typically we've got about 10% of the purchase price per year for maintenance. So if you have a $300,000 machine, you might expect to pay $30,000 a year in maintenance costs just to keep it up and running really well. All right, so let's then think about what would be the machine costs associated with an SLS machine. So let's think about the application that I want to look at today. Okay, let's talk first about the application. Okay. So the application I want to do here is I want to think about building a cell phone cover. Okay, so let's assume we're going to build a cell phone cover, and let's assume that that cell phone cover is for an old iPhone 5, right? And so that cell phone cover that we want to build, right, will look something like this. Okay, and we're going to assume that its dimensions are 12 centimeters, 6 centimeters, by a thickness here of 1 centimeter. Okay, so that's round about the dimensions for an iPhone 5 case. Round it off a little bit. Now we're going to make this case very customized and complex. It's maybe shock absorbing, for example, we'll add into the case. And the other thing we want to do is we want to build as many of these in a particular build as we can. So we're going to think about a full build, a full SLS build of these iPhone cases. We're really going to pack them in. Okay, so let's think about if we could pack these into an SLS build chamber. All right, how much space would they occupy, right? And so this is our application. This is going to build up to our machine, material, and labor costs. All right, so let's look at a top-down view of an SLS build platform. Okay, so this is the SLS build envelope. Okay, and this is a top-down view of it. Okay, so that means that this is X and this is Y, right? And Z here is out of the plane. Okay, so we're looking down at the top view of this build envelope. Okay, so we know that one of the dimensions here is 32 centimeters. Okay, we know that another dimension of this is 37 centimeters. Okay, we also know that the height or depth is 44.5 centimeters. Okay, now so that means that if we want to put these iPhone cases into this platform, one of the things we could do is we could, for example, add 2 of these cases. Oops, let me move this over just a little bit. Okay, so we really want to be able to back away the outer 1 inch of this build envelope. So we don't want to build in the outer 1 inch. So that means that our buildable area here is a little bit smaller. So we have to take away 5 centimeters, which is about 1 inch on each side, and that becomes our buildable area. And so then this area becomes 32 centimeters. Okay. And then we're going to be able to place as many of these iPhone cases in here as we can. So if the iPhone cases are 12 centimeters long, then that makes a good opportunity to place a couple of them in here, right, along the width, right, because they're 12 centimeters long, and 12 plus 12 is 24, and that gives us an extra 3 centimeters there to be able to fit those in. We also know that they're 6 centimeters wide, and so that means we should be able to fit 5 rows of them into the 32 centimeters that we have. They'll be pretty close to one another, but we ought to be able to do it. There's 1, 2, 3, 4, 5, right? We'll do the same thing over here. Okay. And so that means with every layer of these, we can fit 10, so 10 cases per layer. Okay. And if they're a centimeter tall, we probably should have 2 centimeters per layer of build height, just to be careful, right? To leave some space above and below each case. So if that's the case, and we have 44.5 centimeters of height that we can work with, we need to subtract 5 centimeters of that so that we have an inch on the top and an inch on the bottom that goes unbuilt, which leaves us with 39.5 centimeters. And if we need 2 centimeters per layer, then that implies that we can do 19 layers. Okay? If it's 10 cases per layer and 19 layers of them, then that implies that we can do 190 cases total per build. Right? 19 layers of cases per build. Okay. 10 cases per layer. 190 total cases that we can build per layer. So the question we have to ask ourselves is, what is the cost per layer? Or what is the cost per case? Okay. All right. So we want to estimate first, so there are 3 components to that, right? The first is machine costs. The second is material costs. And then the third is labor costs, okay? So let's start out with number 1. Let's start out with our machine costs. Okay. So we had just said that an SLS Vanguard machine that we have downstairs is about $300K, right? Okay, and that's the one that we have in ETC, right, on our ground floor. All right, and so we had also said that, so that's the first thing we have to think about. We also have to build in, so if we think, so what are the machine costs then? Right, so if we assume a 10-year life, okay, with $0 salvage value at the end of life, okay, then that means that our machine costs are about $30K per year. Machine capital costs. Okay. The next thing we have to do is we have to assume, let's assume a 10% of machine cost for maintenance. Okay, and so this is regular maintenance, making sure that seals work and are replaced regularly, that the laser windows are clean, that the laser is calibrated, the IR sensors are calibrated. And so that's going to be another $30K per year of maintenance costs. Okay. Then we also have maybe operating costs just for the machine itself. And that could be, for example, nitrogen. Those are, expendable supplies. And I'm going to assume here that that might be, say, 20K per year if it's running a lot. Okay. So what does that add up to? That adds up to, we've got 30K per year for the machine itself, because we've got a $300,000 machine with a 10-year life. So 300 divided by 10 is 30, if we assume no salvage value at the end of life. And then we've got 30K per year in machine maintenance cost, another 20K in operating costs for running it a lot. And so that's going to be 80K per year total machine costs. Okay. Now, the question then becomes, how many builds are you going to be able to build per year? So let's assume a service bureau with a large part volume, so that we can continue to fill up this machine with builds over and over and over again. And so usually with a full build, it takes at least a couple of days to run a build and clear it out and get ready for another build. So if you're working on the machine and working in the facility 5 days a week, you probably should be able to run 2 builds a week. And let's assume it's down a couple of weeks for maintenance. These are fairly generous assumptions. That could give you 100 builds per year, right? And so that would mean that at 80K per year in machine costs, 100 builds per year, then that's going to say that we've got 80K divided by 100 builds equals about $800 per build just for machine costs. Okay, and I'm going to box this value because we're going to need it. Okay. All right, so running an SLS machine, because it's expensive and it has a finite life, it's going to definitely cost us a little bit of money. Okay. All right. So the next thing we want to think about, right, is material costs. And so let's take a look here. These are some of the costs associated with different types of materials. Right. We'll look at this. And so here you can see for SLS powder, which we're mostly focusing on here, nylon 11. 3D Systems academic pricing for that is going to be maybe $70 per kilogram. You can get lower pricing, about half that or so, from third-party suppliers. So that would knock it down to about $30, $35 per kilogram. It does take at least 30 kilograms for a full build. So that's going to help us figure out how much material we need to be able to fill a build chamber. It's probably best to estimate something like 40 kg just to be safe, right? With a little bit of overflow, a little bit of extra material. Now, how does that compare to other materials? So stereolithography, those machines often are not, sometimes aren't quite as expensive as SLS powder, but materials themselves can be very expensive. So $75 to $200 or more per kilogram. Usually those resins are sold by the liter or by the gallon. I just looked today at prices for Formlabs resin, and those commercial prices were somewhere around $150 a liter. And if there are 4 liters in a gallon, that would translate into $600 per gallon, right? So it can be quite pricey to get that material. You also, FDM filament, it can be very cheap, right? If you buy it for desktop machines, especially if you buy it from third-party suppliers. But for Stratasys machines, the commercial machines, those machines typically require a chip in the material spool so that they verify that it's actually Stratasys materials you're using. And without that, you cannot run the material. So that way they make part of their money from the material and not just from the machine. And so they also know how much material is in a particular spool. So once you scan the chip, you can only build so much, and then it knows that the spool should be empty. You can't go back and cheat them and rewind the spool with a third-party material. And so there, you're paying a huge premium in many cases for the materials that you're using because you have to buy it from Stratasys. Last time I checked, it was pretty pricey. Ultem in particular is a high-grade, high-strength aerospace-grade material, so that definitely comes with a premium per kilogram. And how does this compare if you wanted to injection mold ABS, for example? Those pellet prices run somewhere around $1 or $2 per kilogram, right? So we're really talking about an order of magnitude in more expensive raw material for additive manufacturing, sometimes 2 orders of magnitude than it is for conventional processes. So we've definitely got material costs to deal with. All right, so let's add that to our notes, and let's do number 2 as material costs. All right. So remember, we had said that it could be $70, $75 a kilogram. Let's assume nylon 11. Okay. And one of the reasons I want to assume nylon 11 is because nylon 11 tends to be a lot more ductile than nylon 12. And so if I were going to make an IFOD case and I wanted it to be a little bit shock absorbing, I would choose an 11, I think, over a 12, nylon 12. So let's assume that, and that it's from a third-party supplier. Arkema, ARK-EMA is one of the suppliers we often use here at UT to get material. So then let's assume that we can get it for $30 per kilogram, whereas I said it was 70 or 75 from 3D Systems. So the third-party suppliers are usually cheaper. So we'll assume it's $30 per kilogram. At least, let me write this out so it's easier to see. Terrible handwriting. Okay, and I'd also said assume 30 plus kilograms for a full build. Let's assume 40 kilograms to be safe. Because you'll have a little bit of overflow from the build and those sorts of things. All right. Now, one of the things that's built in here, if we think about $30 per kilogram as a price, that's sort of an academic pricing. I suspect, I'm quite certain that large customers like Stratasys Direct could get their powders for a lower price because they're buying them in bulk. Just as if you buy, small amounts from 3D Systems, for example, the commercial supplier is going to be a lot higher. I think you could get it a better price if you were buying in large bulk. You can also find some even lower cost suppliers, but you have to be really careful because some of them can sell poor blends with some impurities in them. Those impurities can outgas as you're building your parts and cloud, for example, the windows that the laser travels through and cause other damage to your machine. So it's definitely something to think about who the supplier is and whether that supplier is trusted. All right, so we're going to do $30 per kilogram, 40 kilograms of it to be safe. Can we recycle? Okay, so for nylon 12, typically yes, we'll do 50% virgin or so, somewhere around that. And then somewhere around 50% recycled. For nylon 11, it's very difficult to recycle, so you're typically doing 100% virgin on nylon 11, okay? And so for material costs, we're going to assume a full build, right? And we're going to allocate costs of material based on that full build, right? So if we need a full build, it's $30 per kilogram times, we're going to assume we're going to need 40 kilograms, and that's going to be $1,200 per full build. All right. If we were going to 100%, so this is 100% virgin material. Okay. For, say, a nylon 12, virgin nylon 11 material. For a nylon 12, for example, with 50% recycled, then you'd be able to recycle half of what you need, and the cost would be more like $600 per build. So you could make it quite a bit less expensive. But let's box this value because that's something we're going to need later. It's going to cost us somewhere around $1,000 or so to do a full virgin build in nylon 11. Right? Okay. Material costs. Any other material costs that we're not considering? So for other processes, you might also want to include other material costs could include that we're not considering. Maybe cleaning supplies, right, to be able to clean the machine. You might need paint, you might need adhesives, and other things like that to be able to build your final part. So we're not going to include those here because for these cases we don't need them. Okay. All right. Material costs done. Right, and so that's for SLS. If you had something like an SLA, stereolithography, you'd also need to account for support material. You'd also need to account perhaps for other cleaning supplies. You typically wash the parts afterwards and put them in a UV oven. Same thing for, say, an FDM part. You'd have to consider support structures and things like that as well. But we don't need to consider those here. All right, so let's look at the next cost is labor costs, right? So skilled technicians are expensive. Even here in Austin, you know, you're probably going to pay at least $20 per hour in salary, probably more if the person is skilled. But we're talking here about the person who's kind of loading the powder in the machine, and then when the machine is done, taking the parts back out and cleaning them up. They need to be bead blasted. They need to be taken out of the build cake, bead blasted, and prepared for shipping to the customer. So I would say at least $20 per hour in salary, probably more, and that would be assuming you have a technician running this. If you have a BS level engineer or a master's level engineer, it would be a lot more expensive. And then in addition to that $20 per hour, just as a guesstimate, let's add 100% of that salary for technician related overhead. So in addition to what you actually pay the person, you also have to pay insurance, medical insurance, all the Social Security, all those things, provide office space for them, maybe even garments for them, and so on and so forth. In terms of the technician time per build for polymer SLS, if this is a full build, right, you're going to need some time to set up the machine. So you have to load the powder, you have to position the parts in the software, you have to start the build and monitor it. You're going to need some time to break out the build, so remove the parts from the powder, bead blast them, sieve the remaining powder and get it ready if you're recycling, say nylon 12. And so that's just to set up the machine and break out the build when it's done. And it could be longer to break out the build if you have complicated parts that need special treatment, especially if they need to be painted or surface finished, or if metrology needs to be done on the parts. And then it's going to take some time for custom design consultation if you need to redesign for AM, those sorts of things. So if it's 4 hours and 20 times 2 is $40 per hour, then it's at least $160 per build in technician labor. Plus, you know, if there's extra time, if there's lots and lots of parts in there and they all have to be bead blasted and powder removed, it might take some extra costs in terms of labor. All right, so let's go back to our notes and add that in for our build. So step 3 here, labor costs. Okay. So if we've got a skilled technician, $20 per hour for salary, plus another $20 per hour overhead costs associated with the technician, means that the full cost of that technician is $40 per hour, right? It may be more. Lots of technicians make more than that. Per build, let's assume setup. Let's assume that's 2 hours. Let's assume breakout. We just said that we had 190 iPhone cases, right? So we said the minimum was 2 hours, but I think we also need to add some more time to that because it's going to take more than 2 hours to break out all of these parts, right? So let's add a little bit of extra time, and let's add another 6 hours, and let's do a full. Let's add another 8 hours, right? Just to get all those parts. There's so many of them ready to go, right? So that's let's add another 6 hours. I think 8's a bit too much. Let's add another 6 hours, so 8 hours altogether, right? And so that is going to total a total of 10 hours, right? Get everything ready, times $40 per hour is going to be a total of $400 in labor costs. All right, so let's box that because we're going to need that again as well, right? Okay. Now, so let's think about this other, labor costs. Where can some of these labor costs come from, right? So other labor costs that you might have to consider depending on the process, right? So in the pre-build, there are some things to think about, right? You have to plan there's process planning, right? So that could include orienting the part, positioning the part, scaling the part, setting other process parameters, generating support structures, those sorts of things. You've got to load material, run diagnostics, right? So in a desktop FDM machine or any FDM machine, you might need to level the build platform, get things ready to go, clean, etc. Right? During the build itself, you may need to monitor the build. Right, check on it every so often. Restock materials depending on the process if that's something that's needed. Post build, you've got finishing. Right, so you may need to remove support structures, sand, weed blast, machine. Right, if you've got a metals part, you may need to machine it off the build platform. You've got extra post-processing, which could include, cleaning. Well, in this case, you may also want to, you want to paint, assembling. You might have to do additional curing, like for SLA. You may have to do additional sintering, right? For SLS or EMLS, you might need to HIP, for example. Heat treat, right? Depending if you're doing it in-house. All those things might come into play. So it depends on, what you need your technicians to do, right? Okay. So that takes care of our labor costs. And so the next thing we want to do then, we'll go back here to our notes, is to add up all these costs, right? So let's think about total cost. Machine plus material plus labor. And we said for this particular build, we think that the machine costs are going to be $800 per build. The material costs are going to be, what did we say? Those are going to be $1,200 per full build. plus the labor costs we decided would be about $400, all per build, right? And so that adds up to a total of $2,400 per build. Now, if we have 190 cases, iPhone cases per build, then that amounts to a total of about $12.63 per case. Okay, that's the cost. Now that cost excludes profit, it excludes other overhead, right? And so that is things like rent, utilities, so on, right? The cost of shipping and keeping the lights on and legal help and other things like that. And it also excludes, so first it excludes other overhead, it also excludes profit. Right? So we'd probably expect the selling price for this to be maybe about double the actual cost, right? If we look at iPhone cases on, say, Shapeways, last time I looked, if you make them with this process, though, they tend to go for somewhere around $20 to $25 for retail. So that makes a lot of sense, doesn't it? That based on our cost calculations, we probably have around 12 or so, somewhere between $10 and $15 in the part, and then we sell it for 20 to 25, and so that covers the extra overhead and provides a little bit of profit for us per part. All right, so that makes a lot of sense. All right, but the only reason it's so inexpensive, right, is that we were able to pack all those iPhone cases into the build, right? Let's go back up and remind ourselves how we did that. We basically packed 10 iPhone cases into the build chamber, right, into the build plane. And then because those iPhone cases were so thin, we were able to build 19 copies of this, right, from the bottom of the build chamber all the way up to the top, which left us with 190 cases. If we decided to run a full build, but we could only do, say, one case, right, then the full $2,400 of the build would be allocated to that one case. Similarly, if you have a part that's so large that it takes up the whole build chamber, right, then you could expect that, you know, you're going to be charged probably a couple $1,000s for that part. Really depends a lot on how much of the build chamber it occupies and how much post-processing and pre-processing is required, right, to get it done. Okay. All right, so let's go back here. So that's costs. Another thing to do is to think about estimating how much build time it requires to build a part, right? And so build time is another thing that is a little tricky to estimate, but we can put some rough numbers on it for sure. And so part of the reason why I wanted to show you this slide, it comes from a paper that's a few years old, but it still roughly gives us a good sense of build time estimation and what it takes to run a part. So typically for each layer of the part, there are a few things that you need to do. So the first thing that take up some time is to add a new powder layer. So this is where the roller is going to roll across and distribute new powder. Then you have to heat up that powder. So the feed chambers are not quite as warm as the build chambers. So as you spread that powder across, it's going to need to heat up a little bit. There could be some time associated with slicing the model and getting the system ready to scan the new layer, although now with modern computing, that's pretty much non-existent. You have to sinter, which involves scanning the part with your laser, and depending on how complex the part is, that could take more time or less time. And then you have a little time delay between two layers, right? Pauses for a minute, let the sintering take place, and then start again with a roll of a new layer. All right, so a couple of things here that can affect the time to sinter a particular layer. So depending on how complex, let's go over here and look, the part is, your laser is going to have to scan across that part. And so it's not just about how much material needs to be sintered, it's also about the path that the laser needs to take. So for example, if it were scanning out this part, for example, right, it would have to take several paths, right? And then it'd have to turn on and off, right, as it scans across this part, right? So it has to make several passes across the part to be able to scan out the part, even though a lot of that part is empty space in the middle. So the more complex the part, the more it's spread out over the build surface, the more time is going to be required for layer scanning. So that's something to think about per layer. It really depends a lot on the complexity of the part. So time per layer, on complexity of that surface, and also the coverage. So how much of that surface area of that build chamber do you have to cover with the laser? So total time also depends on the number of layers. Right, so here's a couple of different scenarios. You have a part, and that part height here is HP, right? So you can see here you've got one part that's being built on top of another part, right? So then the total height of that build becomes H. If you can instead nest these parts in some way and ideally put them side by side, then your total build height then could become something like H here, where H here equals HP, and here H equals 2 HP, twice the build height. So thinking about ways to reduce the height of our build is really important. All right, so let's go back to our notes and let's just do some basic build time estimation. Okay, so it's really difficult to estimate exactly how long a layer is going to require in an SLS machine. A good approximation might be 30 seconds per layer. Some layers may take a lot less because they've got really complex cross sections that have to be sintered. Others may take a lot more because they've got really complicated cross sections that need to be sintered. Other layers may take a lot less because they don't have these complicated cross sections to sinter. In fact, your very first inch of your build envelope is not filled with parts at all, usually. There's a heat shield that is built down there, but most of those layers are empty, so those go a little bit faster. But let's just say it's 30 seconds per layer. We also know that the depth of a layer, the height of a layer is 100 microns height per layer, right? So that implies, right, that if you want to do a millimeter, right, it's going to take you about 300 seconds per millimeter of height, right? Or 5 minutes, right, per millimeter of height, where a millimeter, right, is equal to 1,000 microns, right? So if a 100 micron layer takes you 30 seconds and you need to build a millimeter, you're going to have to do 10 of those 100 micron layers. And so 10 layers are going to take you 10 times 30 or 300 seconds, right? And so that also means that you're going to do, if that's a millimeter and a centimeter is 10 millimeters, then it's going to be 50 minutes per centimeter of height, right? Sintering. Okay. Plus, all right, plus you've got 2 hours of warm up for the machine before you can build. Plus, you've got cool down. And so most folks recommend several hours, sometimes 8 hours or even more of cool down. So often with our machine, after it's done building a big job, we'll let it cool down overnight before we break it out. So for 40 centimeter build height, that's a full build. Right? Then we're talking about 40, right, times 50, 2,000 minutes. Right? which is approximately 33 hours of build time. Plus warm up and cool down. So you're really talking about approximately 2 days for a fully packed build. Right? So it'd probably take you about 2 days to run that fully packed build of iPhone cases that we talked about. Right? So that's a decent estimate, right, of how long it would take to run a full build on an SLS machine. Right? Okay. All right, let's go back here and let's look at costs comparatively speaking of different processes. Okay. So here we've got up here a very simple small part, right? It weighs 3.6 grams. It's so small that you could build 1,000 of these in a single build in SLS. Okay. And what we've got over here is cost per part, right? Cost per part over here. And then the production volume over here on the x-axis. Okay. So one of the things you'll notice here is if you look at injection molding, right, the cost per part drops, right, as you build more and more parts. Why is that? Why does the cost of molding drop? Well, the reason is that you've got a large sunk cost in the mold itself, right? That mold's going to be quite expensive, and you need to build quite a few parts to be able to get value out of that mold. On the other hand, you'll notice that if you look at stereolithography or FDM or laser sintering, that you don't really see a decrease as a function of the number of parts that you build, right? And why is that? Because we don't have any tooling investments. What you'll actually find if you look really closely, if you zoom in on here and you have this axis, let's say we were building iPhone cases, right? Remember how many we said we could fit, like 190? So let's say, for example, if this were 500 production volume, and this is the cost per part. If you only wanted to build one of them, it'd be really high, remember, like $2,400. And then it would go down, way down if you built 190. And then it would go up again, right? If you had to just build one or two more, you'd have to start another build, and it'd go down, right? And that you'd see this sort of zigzag or sawtooth pattern if you had to do that, because every time you have to start a new build, it's another $2,400, right? That you have to average out over those parts. And as you average that out over more and more parts, it becomes less pronounced, right? Which is why the zigzag pattern tends to decrease. But if you're looking at really large production volumes like we are over here, then that sawtooth pattern is kind of lost in the noise. Now, the next question we might want to ask ourselves is stereolithography, FDM, laser sintering. Why is laser sintering so much cheaper than the others? Well, material cost could be part of it, because we did talk about how stereolithography can have high material costs, although you can recycle all of it. All that leftover resin stays right there in the build chamber. FDM can be a little bit more expensive, but that's not really what's accounting for this big temperature change. What's accounting for the big change in cost? One of the big changes in cost, laser sintering is the only system, right, that allows you to nest parts. So FDM, all the parts have to be anchored to the build plate. Same thing in stereolithography. So whereas we can build like 1,000 parts in this laser sintering machine, we can only build, say, 70 or so for stereolithography or FDM. So every time we run a build, we set it up, we build the parts, we take them off the build platform, we get them ready to go, clean them up. That process, every time we run that process, we get 1,000 from SLS. We get 75 from stereolithography or FDM. And so that's primarily what's accounting for this difference in cost. So just looking from a bird's eye view, a little bit larger, Other cost implications of additive. You know, we've touched on some of these, but I think it's worthwhile putting them all in the same place. So versus traditional manufacturing enterprises, what are some of the benefits? There can be lower labor costs, right? Because the builds are reasonably unattended, right? Whereas other machines, especially if they're not so automated, may need to be attended 24/7. There can be faster time to market. You don't have to build up tools to be able to do this. You can go directly from a digital file to a final part, especially if you've already proved it out and you know you can make it. There's less work in progress. The stock is just the raw material in the CAD file and you're making it. You can distribute the manufacturing so you don't have to ship things as far. You can have some sorts of hub or decentralized manufacturing like at service bureaus. You can also do mobile fabrication. I'll show you a picture of a U.S. Army parts hospital soon. You could even put them at retailers like Home Depot, those sorts of places where they would build parts for you. Waste reduction. So in some cases that's true. We can have less scrap. In other cases it may not be. So injection molding, for example, is a reasonably efficient process with 95+% utilization rate of the plastic pellets that go in, very small scrap rates if the process is running well. Whereas for FDM, you're going to have a lot of support material most likely that you'll have to throw away. You can fabricate products in-house next to the assembly line with no transport, so you know that's faster, cheaper, more efficient. And then finally, you can customize, right? They can be body fitting, aesthetic, etc. And that might even help you reduce material. Here's an example of sort of more mobile parts production, and this has been in use for a number of different years. In this case, they're able to place the whole entire system into a shipping container. You can see that shipping container right here with a tip out area on the side of it to make more room for the machines and so that people can walk in and use the machines. Inside, you've got a lens-like machine for adding material plus 5-axis machining. And they've used it in the theater, in the battlefield, in places like Kuwait and Iraq back in the Gulf War. And they've used it since then as well to build lots and lots of parts, replacement parts, and sometimes even improvised parts that soldiers kind of help design in the field if there's something that could help them be more efficient or be safer. So I'll just end with a look at a few of the references. I'll upload some of these. The Hopkinson Dickinson book is available as a digital resource through the library website, but I'll upload the other 2 papers as well in case you want to take a look. But most of the bulk of what is important we already talked about today in this reference. So I'm hoping this will be really helpful for you as you start to do your economic analysis of your parts for the additive manufacturing class. Think about how many you could fit into a build and what would be the labor, material, machine costs associated with that. So we can get a good sense of how much we would have to charge a customer, right, to be able to make these parts using additive.